Here we are. The physics video lecture once again. It's Physics 4B video lecture 8. We are going to wrap up the thermodynamics section and move on into electricity and magnetism. I had a couple of questions about the homework problems from chapter 20, so we'll talk about those first. So we'll begin with chapter 20, problem 44, and chapter 20, problem 45. Then I have a few things to say about heat engines and heat pumps, and then we'll move on. So we have on problem 44 some object here of radius r made of copper, and it's radiating, but actually it's absorbing more than it's radiating because it's placed in an environment that has a higher temperature. So we've got radiation coming in and going out. The net power being radiated, absorbed and radiated, is sigma E A T to the fourth, where the temperature is being measured in Kelvin. Now in our particular problem, this is a copper sphere that has been blackened, so it has an E equal to 1. And because we have T radiating out and T0 radiating in, we could actually say, let's not call this P net. So then P would be equal to sigma E A T to the fourth minus T0 to the fourth. So it's going to be the net power radiated. And in fact, the minus sign is going to dominate because we have 0 Celsius and 20 degrees Celsius, I believe. Okay. But so far, so good. So that's the power, joules per second being radiated. E is equal to 1. Stefan Boltzmann constant. A, of course, is 4 pi radius squared. So the question is, what's the change of temperature of this object? Because it's a solid copper sphere. So we can also ask that question, and we know that we have delta Q is equal to mass specific heat of copper change in temperature. And if we want to call that delta Q over delta T, then this, the rate of change of temperature we're obtaining right here. Okay. So what we're going to do is identify the net change or the net power with this rate of change of temperature. That's time, that's temperature. So this is also P net. Like that. And we're just going to equate these expressions here. So let's see what happens. Yeah, what we're going to do, the minus sign is dominating here. We just need the magnitude. Okay, so we'll take the magnitude of this, or we can switch the sign around just so that that's noted. So what we're looking for is our delta T change in temperature with respect to time, and we're just solving for this power divided by mass specific heat of copper. And we can now plug in what we have here. We're going to keep the e's, I'm just going to leave e there, but e is equal to 1. So we have sigma e. The area is 4 pi radius squared. And then we have the t0 to the 4th minus t to the 4th. That was just the larger of the two. And in the denominator, we're going to need the density of copper. So this is a mass of a sphere, so that's the density of copper times 4/3 pi radius cubed, and then times the specific heat of copper. So I'm going to leave it right there. Maybe I'll say a word or two more about it. Convert everything to meters. So if it's in centimeters, you have to, it's 4 centimeters, 4 times 10 to the minus 2 meters. But notice you wouldn't want to do anything until you'd canceled all manner of things. Okay, so pi out of here, the 4 as well. 3 will come back up to the numerator, and we're going to have just 1 power of r left. So yeah, never plug in numbers until you have to. And E is equal to 1. So you've got the density of copper, specific heat of copper, 7 Boltzmann constant. E is equal to 1. And then these temperatures expressed in Kelvin. Good. So that's an interesting problem. The other one, you know, I can actually fit the other one right here on this part of the board. This one, we were thinking of a light bulb radiating. So I'm just going to rewrite sigma E A e to the 4th power. So we have something at a high temperature radiating power. And we're asked about doubling the power. What we can do, since for this, we're just going to change the power and change the temperature, or change the temperature, change the power, either way, these remain constant. What we can do is write T2 over T1 is equal to power 2 over power 1. Okay? We're just taking the same equation twice. These remain constant. Oh, not so fast. T2 over T1 to the 4th. Okay. Power 2 over power 1. And this was only going to be doubled. Is that right? Checking my paper here. That's right, it's going to be doubled. So we're going to solve for T2. T2 is equal to 2 to the 1/4 power times T1. And they gave you the temperature in Celsius. Okay, you got to convert to Kelvin and convert back again to get the answer that was in the book. But yeah, that's how easy a problem like this is. And again, you see, do not plug numbers in until you absolutely have to, because all it was a 2 to the 1/4 power. Okay, so that takes care of those two problems. Good. And again, if you ever have questions on the homework, just let me know which ones. I'm glad to do them here at the beginning of class. Let's look at the heat engine one more time, because I want to say something about heat pumps. And we can deal with this at this really basic level, principle level, which is nice. So here's what I'm going to do. I'm going to remind us that for the heat engine, we can analyze this schematic diagram in which we have a high temperature reservoir, energy given off at a high temperature to the engine. It kicks out work, but in order to cycle, we have to have QC dumping heat into a low temperature reservoir. So that's the schematic. And we had as our efficiency work per quantum of energy that we bring into the engine at the high temperature. And we also had the maximum possible efficiency based on the second law, based on first and second laws of thermodynamics. 1 minus Tc divided by Th, temperature of course being measured in Kelvin because this was simply due to the entropy law. So yeah, if you combine conservation of energy and increase of entropy, you get this maximum conceivable efficiency. Okay, so what about refrigerators and air conditioners and things like that? They work on a very similar principle here. So what we're going to just do is draw the heat pump schematic, and it's actually identical to this one. Okay, remember, this was just conservation of energy and increase of entropy. Those are two laws that cannot be violated. But what we can do is reverse the direction of all of these arrows while maintaining those laws. So if you want to get energy to flow from a cold to a hot temperature, or from a lower to a higher temperature, you have to put in work. This is why your refrigerator functions as long as it's plugged in. This could actually be a refrigerator here, and this arrow, if we reverse it, we're bringing in energy from outside and driving a motor. Okay, that's pumping a gas, compressing a gas, and you have a cycle of compression and the decompression that allows you to carry energy from lower to a higher temperature. As soon as you unplug your refrigerator, it's over, right? Then all temperatures equalize and everything is the same. So for the heat pump, we're literally just going to reverse these arrows and do the same analysis we did before. So I draw this thing with the reversed arrows, but I don't have to draw it as large. We'll leave a little room. Well, it's the same picture. Here we go. So the idea is we have some source of energy from the outside, some source of work, and we're driving that motor here. Now you have to come up with some kind of cyclic process that will actually take the, so QC, QH, but you can see the goal, TH. The goal is to get this QH to get some thermal energy that you want to use. So you're putting in work and obtaining thermal energy. Here you're putting in thermal energy and obtaining work. Okay. So heat pump work and thermal energy. Now you could say, well, we had this direction of our what would we call it, of the mechanical equivalent of heat. So we had this direction before, and we just said it was friction. You know, you rub your hands together and things get warm. However, what we're going to see is you can get what's called a coefficient of performance that is vastly greater than just turning the work directly into thermal energy, because you're actually extracting it from a reservoir and moving it from one place to another. So let's go ahead and have a quick look at that. And this is actually independent of all particular cycles. Now the Carnot cycle is the one that allows one to realize the maximum amount, but the principle is independent of that cycle. So what we're looking for, move thermal energy. This is not the same as just creating it via friction. So we want to move thermal energy from the low temperature reservoir to the high temperature reservoir. And the criterion is really just the inverse of this. So what we say is the coefficient of performance, and that's just abbreviated COP. It's the inverse of this. Up here we wanted, we were putting in heat, we wanted to get a certain amount of work out at the highest possible efficiency. Here we're going to invert that. So that is the amount of heat we obtain divided by the work we put in. And as such, this wasn't necessarily less than 1. This can be far greater than 1, especially in principle. Okay. And remember, this definition along with this was for the ideal engine. For the ideal engine, this would involve conservation of energy. Okay. This came from conservation of energy and an increase of entropy. So I should put a note here. I said it, but I'll make sure it's written down. So these things were obtained from conservation of energy and, you know, at the time we said that was QH equals W plus QC, and increase of entropy. So these are the first 2 laws of thermodynamics, and that was just delta S total greater than 0. And this was identical with energy flowing from high to low temperature. Now that's not going to be violated right now. And I guess I'll have to give a little example to make sure we see how that works. But yeah, if I just invert those, what do I have? I have the inverse. It's 1 over E sub C. Okay. Right? So this efficiency turned into that under these assumptions. So the inverse is simply going to be 1 divided by that. So we can say that, we'll go ahead and solve TH, okay, we'll just take common denominator, TH minus TC over TH, and invert it, so TH over TH minus TC. So we can, under circumstances, that, of course, that's a technical construction issue and involves the other laws of thermo heat transfer and so forth. But under circumstances, we can get a very high coefficient of performance, okay? Because if we can make the denominator small enough, then this number could easily be equal, say, to 10 or so. In fact, what you guys should do is try some numerical examples. In fact, here's a good numerical example. Suppose you want to take energy from a 0 degrees Celsius and bring it up to room temperature. Okay, that would be a good idea, right? You have some 0 degrees Celsius outdoor cold air. You want to actually extract heat from that and bring it up to room temperature. So if we do that example, we'll have something good. Okay. So I'll put a frame around here again. There's our coefficient of performance. The example would be TH room temperature, so 20 degrees Celsius, 293 Kelvin. TC 0 degrees Celsius equals 273 Kelvin. So what do we get? We would have 293 divided by that difference, which of course is just 20, and 2A, that's greater than 14. So 14.5 or so. I'll just write approximately 14.5. So theoretically, again, this is a maximum possible. You get 14.5 times the amount of heat out as you put in work. So that could start being a good thing. But you're going to need large heat transfer surfaces and so forth. So achieving that technically is not easy, but still, it's an important thing here. Now, I guess I owe you a quick explanation of how is it that we're not violating. Remember, this here meant TH, here's my cartoon, right? Energy flowing from hot to cold. How is it that we're not violating that when we reverse these arrows here? Okay. And I'll do a real quick discussion of that. Let's see. Just really quick, you guys can pursue this more if you want. So I will schematically do this for a refrigerator. Okay. So a refrigerator, very schematically, it's a box here. So this is inside, and this is outside, for starters, okay? Then you have some coils that are filled with a fluid or filled with a gas, okay? And I'm just going to do this schematic. Okay, so this is outside, this is inside, okay? These coils are filled with a gas, and we're going to put a motor here. So this is where the work goes in. This is a motor that compresses the gas. Okay, so it's a pump. So compression of the gas. Now I have to do some arrows here. So let's see. This is the direction of the gas flow. Okay. So basically the gas inside, okay, right down there's a gas in these coils, it gets compressed, and because it gets compressed, if you ever pumped up a bicycle tire, the gas actually gets hot due to the compression that's been done by the motor there. And so we have hot fluid here, and therefore you're radiating off heat, okay? So the other thing is up here there is an expansion valve. So you're compressing gas on the inside side here, therefore you're producing a partial vacuum, okay? And this compressed gas is expanded into the vacuum and it cools again. So it cools to a very low temperature. So you've got hot gas on the outside, cool on the inside in these coils. And then whatever the inside temperature is, you've got something inside here, like your carton of milk or whatever it is. The inside temperature of the refrigerator is warmer than the gas inside those coils. So the heat is given off to the coils. Okay. And you can see the temperature is warmer to cooler, and outside here the coils are hot, it's warmer to cooler air temperature in the, say in the ambient temperature of the room. So that's why this law is still maintained. It's because you're putting work in, and this working substance, the compression, the decompression, produces these higher temperature gradients. So yeah, the moral of this story is that this law is not violated But by putting energy in, you can move the thermal energy from inside to outside. So essentially the thermal energy from your carton of milk, whatever is in the fridge, your tray of ice cubes, your tray of water, is moved from inside here to the outside where it's warmer, okay? So that's how that works. In fact, what we could do is we could say we've got the temperature inside the refrigerator, we've got the temperature outside the refrigerator, but the temperature of these coils is much colder, and the temperature of these coils outside is much hotter than this. So that's how we maintain these flows. Good. So that's I think this is the order in which to approach this topic, because there are much more technical discussions, but this was the principal discussion. So we will leave it right there. Okay, good. So from here we're moving on into electricity and magnetism, which will occupy us for the rest of the semester. And yeah, that's a new chapter. I'll erase all this stuff. Okay, good. Electricity and magnetism. So I'm going to start with a couple of general points here. So this is our new chapter, but really it's a whole new section, electricity and magnetism. And I'm going to return to all of the material you did last semester and all up until now here, because what we've been studying so far is all a subset of mechanics. So previously we're studying mechanics. Now this thermal physics started out with just a sensation of hot and cold and some phenomena of fire and so forth. But remember, we did reduce everything to mechanics via work, mechanical equivalent of heat, and basically the atomic theory, okay, where temperature and velocity of atoms were related. So previously we had mechanics and thermal physics also turned out to be part of mechanics. And what we had here in mechanics and thermal physics was forces, work, energy. We had space and time, mass. So mass, space, time, and that's really all we had. And our units were the kilogram, the meter, and the second. All formulas that we've had up until now can be expressed in terms of kilograms, meters, and seconds, everything. In thermal physics, as well as in point mechanics, here it gets pretty interesting. We already had talked about electromagnetic radiation. But the power, which is what we knew about, so we had a power, thermal quantities, power, heat capacity, and so forth. were all expressed in terms of kilograms, meters, and seconds. So part of thermal physics did involve electricity and magnetism, the radiation formula that we just repeated a couple times early at the beginning of class. But again, it's all just in terms of these quantities, and for the first time we're going to introduce a new one. So now we're going to introduce one more quantity called electric charge. Electric charge, and as we'll see, it comes in two flavors, so to speak. It comes in positive and negative, plus, positive, minus, and here, that's not an equation, minus, negative. So positive charge, we often use the letter Q for that charge. And the unit is the Coulomb, right? It's something completely new. We can no longer express it in kilograms, meters, and seconds. The unit is the Coulomb. So I'm going to have to back up a bit and describe these a little more. But the point was being made that we now have kilograms, meters, seconds, and coulombs, which will just be a capital C. Okay, so how do we discover electric charge? Experimentally, and I could possibly bring some in, but you guys should look some of this up or actually experiment yourselves. We're talking about static electricity. So static electric phenomena these are the little shocks and sparks that you experience when you pull off clothes, walk across a carpet and touch something. You could rub a balloon against the wall and then let go and it'll just hang there. Those are static electric phenomena. So all these little sparks and then things that cling because they've been charged. This is you feel something here if you're subjected to it. If something hangs off the wall when it should actually be falling, there must be a force involved. So we know there's a force involved. And the static electric demonstrations and experiments are about generating enough of this phenomenon so that you can actually measure it. So this is something you guys should look up. And I'll try to bring some in next time as well. Look up static electric demonstrations. In addition to the ones that you've already seen, the fact that there is seen and felt, the fact that there's a force involved, as soon as something sticks to something else, right, you have to exert yourself to pull it apart, there's a force. So the fact that there's a force involved is what we're interested in. We're interested in finding the law of the force, okay? So what is the force law? So it turns out it's possible to get things to attract or to repel. So we have two kinds of charge, positive and negative. And the first part of the law is simply that like charges repel and unlike charges attract. So that's the first thing about the force law. like charges repel, unlike charges attract. Okay. So yeah, if you have a plus and a plus right here, they're going to be driven apart. And if you have a plus and a minus, and the same for a minus and a minus. Here I'm separating these. Minus and minus are also going to be driven apart. And then a plus and a minus, positive and negative, are going to be attracted towards each other. Okay? And it'll be a force, so something you can feel. So at this point, we don't know anything about electrons and protons and neutrons yet. Okay? We're generating these different charges, plus and minus, with friction, and we're applying them to little experimental objects. So I'm going to even start, I'm going to describe an experiment that can really be done for the force law. So, well, here's what we'll do. Coulomb's law, we'll write down Coulomb's law. Coulomb's law for point charges. And a point charge doesn't have to be that small if it's a little spherical dot or spherical object. But Coulomb's law for point charges is discovered in the following way, or can be measured in this way. Suppose you have two pendula. Okay. Well, actually, let's do this. So suppose we have these two masses, and they should be hanging straight down. Okay. We've got gravity pointing down right here. We've got these two masses. They should be hanging straight down, but they both have charge on them. They both have, say, a positive charge on them, so there's a repulsive force. Okay. So let's just say we have Q1 and Q2, and they're both positive. So there's going to be a repulsive force pushing them apart. What color should I use? Well, I'm going to use red for all these forces. So we have a repulsive force pushing them apart, and of course there's the gravitational force pulling them down. This is going to be a homework problem, by the way, but I'm going to set it up for you. So here we have this known weight, mg and mg, and put an angle theta there since it's a symmetric situation. And now we could do experiments if we could have more charge, less charge, and measure the way the angle varies. We can also change the mass here. So we can do a series of experiments in trying to discover what that actual law is. First, at the beginning, we just know there's repulsion. Okay. So Coulomb's law for point charges is the following. Let's just say we have Q1, Q2 separated by a distance r. First thing about the law is it's a central force. It's a central force law, which means the force is either, like I said, attractive or repulsive, but along the line joining the two charges. Okay, that's what it means to be a central force. Its magnitude is equal to a constant times the product of the two masses divided by r squared. Which is amazing because it looks just like Newton's law of gravity. Except it can be positive or negative, it can be attractive or repulsive depending on whether these are like charges or unlike charges. And so this is k sub e, we'll call it, this is a constant. There's another way of writing that constant, 1 over 4 pi epsilon naught q1, q2 over r squared, that's times. And you can see these are just two equivalent ways of talking about it. This is a natural constant, epsilon naught is a natural constant. So we have to be prepared to see either one of these. Okay. So here's where we have to bring some numbers into play finally. Central force law, 2, this is the magnitude. And I'll say central force law, attractive or repulsive. Attractive or repulsive. So now we have to know what these constants are here. Ke and epsilon naught. These are just numbers, I have them here somewhere. So let's see here. 8.99 times 10 to the 9. What are the units? Okay, we should always remember to tease out the units. So this is a force, it's newtons times meters squared by cross multiplying divided by Coulomb squared. So Newton meters squared divided by Coulomb squared. And epsilon naught will be the inverse of that, right? Because it shows up in the denominator. So epsilon naught is going to be 8.854 times 10 to the minus 12 Coulomb squared Newton meter squared. And of course this K is equal to 1 over 4 pi epsilon naught. This would be simpler, but this epsilon naught comes up in certain formulations. We'll see where this one is simpler. Okay. So I do have to say something about electrons and protons at this point. And their charges and masses as well. So that's the interaction law. So right under these natural constants up there, let's just put down for 3 particles here. So we have the particle, and we have its charge, and we have its mass, and the charge will be in coulombs, the mass will be in kilograms. We have electron, proton, neutron. So the neutron has no charge. The electron has negative 1.6 times 10 to the minus 19 Coulomb. You already realize these fundamental particles, it takes very, very many of them to make up a Coulomb. Okay, because you have 1.6 times 10 to the minus 19. Proton is positive the same thing. Okay, like I said, the neutron 0. The mass of the electron 9.1 times 10 to the minus 31 kilograms. Mass of the protein 1.673. 10 to the minus 27, and 1.675 for the neutron. Very close, but not exact, times 10 to the minus 27 kilograms. Okay, I'm going to consult the clock. Good. So the discovery of these particles and their masses actually requires some more knowledge of the laws that we're going to be studying. The discovery of Coulomb's law does not require knowledge of these things yet. Of course, we're going to work with these immediately, but just in terms of the method or the progression of ideas, generating charge via friction and applying it to different objects and then seeing them separate and so forth. Repel does not require the knowledge of its electron charge or its mass. But I'm going to go ahead and use these anyway, because with these values that we can discover later how they're obtained. With these values, you can make a good comparison between gravity and electromagnetism and electricity, because the force law here can be compared to the gravitational force law. So I'm going to do that next, and I'll do that next, and then I'll set this one up carefully for you, and then we can get a homework assignment going. Okay, because we have these particles with charge and mass now, so the question is, how does gravity compare to the static electric force? So how does gravity, or let's say, how do gravity and electricity compare? We'll just call it electricity. Compare. Question mark. Okay. Here's the idea. Suppose there's a proton here, m sub proton plus E. And suppose there's an electron over here, m sub electron minus E. Okay. So proton, I'll write here proton, electron, and they're separated by a distance r. Well, there's an electrostatic attraction, but if we just think of them as being two masses, like the sun and the moon, the sun and the earth, earth and the moon, think of them as being two masses, then there's also a gravitational attraction. So we want to compare the gravitational and the static electric attraction forces. I'm going to redraw this picture for our homework, because it's good to have all these numbers up here. Okay. So we're just going to take the ratio of the two. So for this system here, F sub gravity divided by F sub electricity. They're both forces, so newtons divided by newtons cancels out. It's just going to be a number. And we know from gravity, we have G, M1, M2, and let's go ahead and say G, mass of proton, mass of electron, divided by distance separated squared. Well, if I'm going to divide that by the electric force, I can just flip that. Right here, when I multiply, it'll be KE E squared. So Q1 times Q2, we have that here. It's the K times Q1, Q2, so E squared over R squared. So that's nice. The ratio of these, the distances cancel. So F sub G over F sub E is equal to the units, so 6.67, that's my G, times 10 to the minus 11 Newton meters squared per kilogram squared. And then we're going to have to multiply these two masses, electron and proton. So we've got the, I have to erase a bunch of stuff here. I'm just going to put these numbers here. You guys should multiply them out. In fact, if you read the book, you'll see the book multiplies them out too. So 9.1 times 10 to the minus 31 kilograms, and then 1.673 times 10 to the minus 27 kilograms. Okay. So all of this divided by 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. And then these two charges squared, 1.6 times 10 to the minus 19 squared Coulomb squared. So yeah, everything is going to cancel, okay, dimensionally. Okay, so what does that equal? Some really big number. Oh, very small number. I inverted these. Tiny number. Okay. I was wondering. I was going to do the other way around. Okay, so this is a very, very tiny number. And you can see that by just adding up these exponents. Okay. The effect is better if you do the big number, but you're looking at, well, let's just look at them here. 30, 40, 50, 58, 69, 70, 69 in the numerator, and about 40, 50. So yeah, it's going to be a huge difference. 27, 11, 30. 19.9. Yeah. So go ahead and do this. The point is this force is enormously weaker than the electric force. So much weaker that it plays no role at all. Okay. It is many, 20, 30, 40 orders of magnitude. Okay. So it plays no role whatsoever. So that's the punchline here. Gravity is much weaker. Much weaker. Let's consult the clock again. Okay, good. want to go back to, now that we know how much weaker that is, much weaker. I'm going to go back to the problem that I had erased and set it up for you guys, and that's what we'll end with. And I'll consult the book just to see how it's formulated. I don't want to solve the whole thing for you, but I will do a good part of it. Yeah, this is problem 74. They're having us solve for Q, length L, angle theta, etc. Yeah. So let's set this problem up again. We have two equal mass, so there's M, equal mass, equal length of string here. We're getting an angle theta equal on both sides because there's gravity and there's the electric force. So there's going to be Q, or let's see, we're calling them symmetric. Yeah, mass M, charge Q. So we have Q on here and Q on here, okay, same charge. So what we want to do is set up the free body diagram. So we know we have symmetry. It's going to suffice, it'll suffice for us to just look at the right side here. We have mg, there is, I'm just going to write F sub E, and then there is a tension here, tension T. So we're just going to analyze the right side. Maybe a while since you did one of these, but I know we did these earlier in Physics 4A. So let's go ahead and give this an X and a Y axis. And then we have in X direction, and by the way, since there's that angle theta, we've got an angle theta right here. So in X direction, what do we have? We have, pointing to the left, minus tension sine of theta, right? Theta is right here, so theta is right here as well. Okay, so pointing to the left, right, that's that one right there. That's minus T sine theta. And what's this electrical force? Electrical force is plus K Q squared, and the separation distance is this distance here. It's twice L sine theta. 2L sine theta squared. That's one equation. Because remember, it's the distance all the way from one particle to the other. It's a repulsive force, so L sine theta to here, another L sine theta to there, so 2L sine theta squared equals 0. So that's one of our equations. And then in the y direction, we have T cos theta minus mg equals 0. So two equations, two unknowns. You can eliminate the tension and then solve for Q. And that's what the problem is asking us to do. But yeah, this is a good one to start with because you can imagine doing experiments with different length, mass. You can vary different things here to try to discover what this law is here, what the Coulomb force is. The other thing to note is that when you actually do this, it's pretty difficult. Okay? It's pretty difficult to control it, to keep the charge from bleeding off, to keep them from just bouncing around. But yeah, that's the reason I wanted to start with that problem. So you've got it set up here. You can solve two unknowns. Have a look at this. You'll see it in your book as well, but you just add up these exponents, you can see what's going on. And what else? Let's consult the time. Okay, that's good. Let's write down some homework problems. I just showed you this last one that was on my list. So I wrote down quite a few. So this is homework 8. We're just numbering them with the lecture. So if we missed one, this is homework 8, goes along with lecture 8. And we have chapter 21, problems 22, 35, 64, 69, A, B, and C, and 74. Good. So we'll leave it at that and have it, like I said, 74 is the one we just discussed. They're all about forces, between different charged particles. One of these, wait a minute. Well, I have another great one, but we'll save that for next time. Good. See you guys next time.